Major American market automakers have, in a very short span of time, all found themselves at the center of serious engine failure crises. We're talking about recalls in the hundreds of thousands. Federal investigations covering well over 1 million vehicles. Billion-dollar settlements. Engines being replaced under warranty, and then failing again the same way. These are not obscure brands. These are the dominant names in the market. The ones people spend $60,000, $70,000, $80,000 on. The ones that line every dealership lot in every state. And they are all breaking down in overlapping, eerily similar ways. Now, I want you to think critically with me here. When 4 separate companies, with separate engineering teams, separate factories, separate suppliers, all produce the same category of failure around the same time period, what does that tell you? It tells you the problem is not internal to any one of them. The problem is the environment they all share. The rules, the targets, the market pressures that every single one of them is responding to in the same way. That's what this video is about. Not the symptoms. The disease. Part 1, the overloaded engine. I want you to picture 2 workers doing the same job. The first one is built for it. Big frame, strong joints, years of conditioning. You give him a heavy load, he handles it without much strain. He could do that all day, come back tomorrow, and do it again for 20 years. The second worker is lean, fast, efficient looking. On paper, his output numbers are impressive. But he's carrying the same weight as the first guy, and his body is working twice as hard to do it. Every joint is at its limit. Every muscle is under constant tension. Give him a good day and he performs. Give him 3 bad days in a row, and something tears. That is the story of what happened to the modern truck engine. 25, 30 years ago, a full-size truck came with a large displacement V8. Big, heavy, built with what felt like overkill amounts of metal. It made moderate power. It breathed easily. The tolerances inside it were generous, meaning there was room for small imperfections, for a little wear, for a bad oil change or a hot summer day without consequences. Those engines are still running today in trucks with 300,000 miles on them. You probably know someone who has one. Here's what changed. Engineers discovered that a small displacement turbocharged engine could produce equivalent or greater power numbers on paper. A 2.7-liter engine with turbocharging can hit output figures that would have required a much larger naturally aspirated engine a generation ago. That looks great in a brochure. It looks great in a fuel economy headline. But here is what does not make it into the brochure. That small engine is operating at cylinder pressures and thermal loads that were historically only seen in purpose-built racing engines. Engines that get disassembled and inspected after every race. Engines that are treated as precision instruments that exist for one purpose and nothing else. Your truck engine is not a racing engine. It idles in traffic. It sits in a parking lot for an hour with the AC running. It gets cold started on January mornings. It tows a trailer up a mountain highway in August. And it does all of that with half the metal of the old engine, at twice the internal stress, with tolerances measured in microns, gaps smaller than a human hair, that must be maintained perfectly, forever, for the engine to survive. Tell me honestly, does that sound like a design built for 200,000 miles? Or does it sound like a design built to hit a number on a test? Part 2, the oil that wasn't enough. This part might be the one that frustrates me most, because the decision-making here is so clear, so documented, and so deliberately obscured from the people buying these vehicles. Motor oil has one non-negotiable job. It has to maintain a protective film between every pair of moving metal surfaces inside your engine. If that film fails, even for a fraction of a second under the wrong conditions, metal touches metal, and wear begins. Enough of that wear, and the engine fails. For decades, the standard viscosity for most engines was thick enough to do that job reliably across a wide range of real-world conditions. Cold starts, hot days, towing, idling, the oil was robust enough to stay in place. Then the pressure to improve fuel economy test numbers created a different incentive. Thinner oil flows more easily, creates less internal drag, and marginally improves performance on standardized fuel economy measurement cycles. So viscosity grades started dropping. And dropping. And dropping. Some current production engines now run oil so thin it would feel nearly indistinguishable from water if you held it in your hands. That is not an exaggeration. That is the actual physical reality of what is lubricating your engine's crankshaft bearings. And here is the critical question: does anyone reading this remember hearing that explained at the dealership? At the oil change? In the owner's manual and language a normal person would understand. I want you to comment below if your dealership ever told you what viscosity your engine runs, why, and what the consequence of going one grade thicker or thinner would be. I'm genuinely curious how many people were ever given that information in plain language. Because here's what the manufacturers know, and what their internal engineers know. Ultra-thin oil only works if every variable goes right every single time. The machining has to be perfect. The bearing clearances have to be exact. The oil has to stay clean and unpolluted. Oil pressure cannot drop, not for a cold start, not for a brief moment of low idle, not ever. In a controlled laboratory, you can make that work. In the real world, at mass production scale, across millions of vehicles driven by millions of different people in millions of different climates, you cannot guarantee that. And the manufacturers knew that. The clearest evidence of this is in the documented recall remedies themselves. In at least one major recall, the prescribed fix was to switch from the factory-specified oil grade to one that was substantially thicker. If the problem were debris, or machining defects, or any mechanical issue, changing the oil viscosity would do nothing. The fact that oil weight was the fix tells you that the original specification was the problem. That the oil was never sufficient for the real-world demands of that engine. And it was sold to consumers that way for years. Part 3, the factory problem. Here's a question worth sitting with. When you buy a new vehicle, what are you actually paying for? Because part of what's supposed to justify the price of a modern truck or SUV is that it was built under rigorous, controlled conditions by experienced people with precise equipment. That assumption has some serious cracks in it when you look at what engine manufacturers themselves have formally documented in federal recall filings. The manufacturing process for a modern engine block involves cutting, drilling, and finishing operations that leave behind microscopic metal particles. In an ideal world, thorough cleaning processes remove all of that material before the engine is assembled. In the real world, especially at the scale of producing thousands of engines per day, that cleaning is imperfect. The particles that survive the cleaning process are small. You would not see them if you looked at the engine. But they are sharp, they are harder than bearing material, and when oil circulation carries them into a bearing gap measured in microns, they act like sandpaper spinning at thousands of rotations per minute. The damage they cause is not immediate, but it is cumulative. And it is invisible right up until it becomes catastrophic. This problem has existed as a background risk in manufacturing for a long time. What changed is that the margin for error disappeared. With older engine designs running thicker oil and larger tolerances, a small particle of debris was survivable. The oil film was thick enough to absorb it. The bearing material in older engines, which included a thin, soft overlay layer, could actually embed small particles harmlessly and neutralize the threat. Modern engines remove that safety layer. The bearing materials used today are harder, cleaner, and in an absolutely perfect environment, more durable. But they are completely unforgiving of any imperfection. Debris that an older bearing would have quietly absorbed now scores the surface directly. So you have a situation where the cleaning standards need to be higher than ever before, at exactly the moment when production scale makes thorough cleaning harder than ever before. And the consequences of getting it wrong are worse than ever before because the tolerances that used to provide forgiveness are gone. I want to ask you something. If you found out that the engine in your vehicle was built during a period of documented quality control disruptions, and those disruptions are in official federal filings, not speculation, how would that change how you think about your maintenance schedule? Drop your answer below. This is exactly the kind of thing worth talking through together. Part 4, the years nobody talks about. There is a specific production window that automotive analysts and mechanics are watching very closely right now, and it corresponds almost exactly with when the volume of serious engine complaints started accelerating. The years roughly spanning 2020 through 2022 were genuinely chaotic for manufacturing. Workforce disruptions, supply chain instability, new or unfamiliar suppliers brought in under pressure, reduced quality inspection capacity, and compressed production timelines all converged at once. The result was vehicles that looked identical to their predecessors on the outside but were built under significantly more compromised internal conditions. What happens to an engine with a hidden manufacturing imperfection? For the first 30,000 or 40,000 miles, often nothing visible. The defect is microscopic. The damage accumulates slowly. By 60,000 to 80,000 miles, which is exactly where many of those 2020 to 2022 vehicles are right now, hidden defects reach a threshold where they produce real, destructive failures. The timing of the current spike in complaints is not random. It is the predictable consequence of compromised production reaching its failure window, right now, across a large portion of the market simultaneously. If you own a vehicle from that production window, this is not meant to alarm you unnecessarily. Many of those vehicles will run without issue. But it is worth knowing that your maintenance habits matter more, not less, than they would for a vehicle built in a more controlled period. Part 5, the restart you do not think about. How many times does your engine start and stop in a typical city commute? Not at the beginning and end of your trip, I mean the automatic start-stop system that shuts the engine off every time you come to a complete stop at a light, a crosswalk, a congested intersection, and restarts at the moment you lift your foot off the brake. If you drive in a city, that number might be 30, 40, 50 times in a single morning. Each one of those events is a micro cold start. Oil pressure drops to zero the moment the engine shuts off. When it restarts, there is a brief interval before full oil pressure is restored. In that interval, the bearing surfaces are in contact without a complete protective oil film. With thicker oil and softer bearing materials, the residual oil film from the previous cycle is enough to bridge that gap. With ultra-thin oil and hard bearing materials in a turbocharged engine running at high stress levels, that same brief interval causes measurable wear every single time. Over 100,000 miles of city driving, those events accumulate into something significant. This is why vehicles with similar odometer readings can be in dramatically different condition depending entirely on how they were driven. A truck that spent most of its life on open highways, with rare stop-and-go cycling, is genuinely less worn internally than one with half the miles driven entirely in a city. The odometer does not tell the whole story. The number of start cycles does. If your vehicle has a manual disable button for the start-stop system, use it every time. If it resets every time you start the car and that frustrates you, there are inexpensive plug-in modules that can disable it permanently without affecting anything else. The fuel economy difference is negligible. The impact on bearing longevity is not. Part 6, the rule that started all of this. Everything we have covered so far, the downsized turbocharged engines, the ultra-thin oil, the razor-tight tolerances, the start-stop systems, the cylinder deactivation technology, all of it has a common origin. None of it came from engineers deciding these were the best ways to build a durable engine. All of it came from regulatory fuel economy targets that carry enormous financial penalties for non-compliance. The math on those penalties is not subtle. A manufacturer missing fleet average fuel economy requirements by a meaningful margin faces costs that can reach into the hundreds of millions of dollars annually. Against those numbers, the projected cost of warranty claims, recalls, and settlements from reliability compromises becomes a line item in a spreadsheet. A manageable one. A calculated one. I want to be clear that I am not suggesting individual engineers made reckless decisions. I am suggesting that the system those engineers work within created incentives that made reliability a secondary priority. The engineers who understood exactly what compromises were being made were overruled by financial constraints that left them no other option. Some of them have said as much, in various forums, over many years. The result is that an entire generation of vehicles was built to perform well under controlled testing conditions, to survive the warranty period with an acceptable failure rate, and to leave the long-term consequences to the consumer. Is that a criticism of the manufacturers? Yes. But it is also a critique of a regulatory structure that created the incentive in the first place, and of a market that rewarded impressive power-to-MPG figures on a window sticker without asking deeper questions. If you have thoughts on this, whether you think the manufacturers are primarily responsible, or whether you see this as a regulatory failure, or both, I genuinely want to hear your perspective in the comments. There is no single clean villain in this story, and that is part of what makes it so complicated and so worth discussing. What you can actually do. Knowing the structural causes of these failures does not reverse anything that has already happened. But it does let you make smarter decisions going forward. First, check your vehicle identification number against the National Highway Traffic Safety Administration database. If you are in a recall window, get the repair done. Do not wait. The failures that these recalls address frequently occur without warning. There is no gradual degradation phase where you get to see the problem coming. One day the engine runs, and the next day it does not. Second, shorten your oil change intervals meaningfully. Whatever interval the manufacturer recommends, cutting it in half is not excessive given what we know about these engine designs. The cost difference between 4,000-mile and 8,000-mile oil changes over several years is small. The cost difference between consistent maintenance and an engine replacement is not. Third, if you are shopping for a used vehicle and reliability is your priority, give serious consideration to older naturally aspirated engines with longer track records. A well-maintained older large displacement engine with high highway miles is not automatically a worse choice than a newer turbocharged engine with low city miles. The newer technology is not inherently more reliable. In the current generation of vehicles, there is a strong argument that it is less reliable. Finally, talk to your mechanic honestly. Ask them specifically about the failure patterns associated with your engine. Ask them whether there are proactive maintenance steps beyond the owner's manual schedule that they would recommend given what they are seeing in the shop. The people doing hands-on repair work have a ground-level view of what is actually failing and why that no manufacturer communication will ever fully capture. Final thought. Here is what I want you to take away from all of this. The failures happening right now across the market are not random. They are not bad luck. They are the predictable outcome of a specific set of engineering trade-offs made under specific financial and regulatory pressures, catching up with a specific generation of vehicles at a predictable point in their service life. Understanding that does not make it less frustrating if it happens to you. But it does mean you are not powerless. You can maintain your vehicle more aggressively. You can make smarter purchase decisions. You can push back when a manufacturer or dealer tells you a failure is isolated or unusual. And you can talk to other people going through the same thing. So let me close the way I opened. What do you drive? Has any of what we covered today matched something you have experienced or heard from someone you know? Drop it in the comments. The more people share what they are actually seeing, the clearer the picture gets for everyone watching. If this gave you something useful to think about, share it with someone who is currently shopping for a vehicle, or someone who just bought one and has no idea any of this is happening. That is the most useful thing you can do with this information. More coming on this topic. There is a lot left to cover.